Welcome back, everybody. This video is going to be about single slit diffraction and the diffraction grating. So we have now seen what happens when waves interfere and what happens specifically in the case of a double slit setup. But you may wonder what happens if you simply have a single slit arrangement. That is to say, you've got a long barrier, a hole, and then there's a long screen on the end. And, again, this is something you could do with water waves or sound waves or any other kind of wave. Imagine that you're sending in waves. They are purple waves, just for illustration. Long plane waves. And remember, they're coming through, they're traveling in this direction. And the spacing between what I've illustrated here, I've illustrated a bunch of crests, and that means that this is the wavelength. And the separation between that the single slit screen and the screen on which the image will show up, or the pattern will show up, whatever it is, that separation is L. And so if you haven't already read ahead in the book, and I know you all have, you might predict what does the intensity or brightness look like on the screen. So there might be three things that you might imagine. So let's just imagine what happens. What happens? Can you predict to intensity pattern? Waves come through, and they're set up. I'm going to go ahead and define a variable at the moment. I'll call this D, the single slit opening. There are three things that come to mind. One is that if I were to draw the intensity as a function of position, or I'll call it brightness, one is the simple-minded prediction, and that is to say that there would be no brightness at places that were above the hole opening and below the hole opening. In other words, the brightness should be 0, 0, 0, and then a ton of light should come through, and then 0, 0, 0. That pattern would correspond to, right, all these waves, this stuff coming through and nothing coming through over here, and so it gets blocked by the time you get to this side. So it should just be some pattern that looks like that, like I drew. That's one prediction. The other prediction might be, well, we know that light can be described by a wave, or we're doing any kind of wave, so maybe it's a bit more spaced out. That would seem plausible. So maybe it's got like kind of a, maybe it looks like a Gaussian, so this stuff comes through and it spreads out, and so that results in, this kind of pattern. And there's a third option, in case those aren't true. And they're not. So maybe you should think about what that third option is. Pause the video if you feel so inclined. But I'm going to now cheat and take a video of a video. This is what happens.
Slit diffraction. When
Single
a
slit
laser
diffraction.
beam, I'm putting my hand in the beam here. This laser beam is incident on this circular dial that allows me to dial in the width of a slit through which the laser beam passes. So it's passing through this slit of various widths that I'll show you, and then having passed through the vertical slits, produces a pattern on the screen here. So,
okay, punchline. We can stop talking now.
The width,
Shush. You see that there's a bright central spot, and then it goes dark, but then you get more bright spots.
This pattern is a central bright spot, and then dimmer spots to either side. This is called the M equals 0.
This might be a good video to watch if you're trying to go to sleep. That's the punchline. So let's just see if we can understand why in the world it works out that way. Ooh, Stoicism. Space isn't empty. Which one is better? Oh, wow. Okay, I'll come back and watch those videos later. Okay. What is this called? Single slit diffraction, WTF. How does it work? Oh, I have a slide for that. Thank God. So, how does single slit diffraction work? How can we understand it in terms of this wave model of light? well, it's helpful to think about this in terms of Huygens. So, wave, rays, whatever, when you just think about what's going on in the center of this interference pattern, you get I'm back. Let's see. Okay, you get stuff. So let me draw the little sources of wave, right? You can do this at any point along the wave front. Each little wiggling, jiggling piece of electromagnetic field can create its own wave. That's the way we can think about this according to Huygens. Creates these little wavelets, and those, the envelope of all that is the wave that goes out and makes the central bright spot. Fine. But we can also think about what happens as we look at a slightly different angle offset from the center. And that's what this second picture is about. So you can imagine looking downward, and imagine that you're looking downward at an angle theta, and this angle is such that, the distance that this first wavelet would have to travel, the one that's emitted from here, and goes out this way, is a full wavelength longer than the one that's emitted from the bottom of that slit. And so you might guess, well, that one's offset by a full wavelength from this one, and so wouldn't that make constructive interference? Yeah, those two would, but you've got a lot of stuff in between that you've got to add up. So let's actually do the math a little more carefully. Let's instead focus on what happens when we consider a little wavelet, if you like, coming from that point, and a little wavelet coming from this point halfway down. So if this here is a full wavelength longer than what you get from this point here, that means that it is only half of a wavelength longer than this wave here. In other words, the distance, this length compared to this length, they differ by half of a wavelength. So those two wavelets that come out of those two spots, since they're offset by a half a wavelength, in other words, a crest matches up with a trough, those will make destructive interference. So let's just keep things together. That's destructive. But, there are actually many pairs, in fact, an infinite number of pairs you can identify. Notice then if we go with the next one down the list, so let's say this one, and the next one down the list over here, there, those two will also be, will have path lengths that differ by a full wavelength. So let me try to draw this over here. These will also add up to be destructive. In fact, all such pairs that you can combine till you have captured everything here will result in a destructive pattern. Okay, remember what we had found in one of the previous videos, that angle theta, d sine theta, well, it's equal to, according to this diagram, it's equal to lambda over d. D is the hypotenuse. And that gives destructive interference. Well, according to this formula, that would also be true if it wasn't offset by lambda, but if it was offset by 2 lambda, the math would also give you destructive interference. So that's what's going on in this picture here and in this picture there. Bright spots would appear as well. That turns out to be just slightly more complicated when this path length is a half integer. But the main summary here is, if you like, so this formula works for this example. This formula works for this example when sine of theta is equal to 2 lambda over d. The moral of the story is that when you have single slit diffraction, you'll end up with the location of dark spots whenever d sine theta is equal to m lambda. So this is the location for dark spots with single slit diffraction. Okay, save, sure. Good. What does this all mean? So let's think about building this up. I think is what I want to say. So single slit, right? So if you have a single slit, what you're actually going to see is, again, the central maximum, and then you'll see a minimum on both sides, and then you'll see another maximum that appears. Of course, it's smaller in amplitude. We were not talking about why it's smaller in amplitude, but you do get another maximum that appears there. And I think what this does is this leads us into, so we've now talked about what happens with one slit, and we've already seen what happens with two slits. So let's kind of build this up and see what happens when you end up with many slits. So one slit does this. Two slits we've already seen, and this is illustrating that you get these maxima and minima, and this dotted line represents the sort of envelope of what we got in the previous picture with one slit. You can imagine putting three slits in between, and notice what's going on here. I'll go one more. I'll go to 5 slits. Notice that as we move from one slit, which has, big peak in the middle followed by, and it's wide. 2 slits, you've got fairly narrow peaks. 3 slits, even more narrow and highly concentrated. 5 slits. And so what this works up towards is something called a diffraction grating. When there are many, many slits, that is called a diffraction grating. And what you can, are there any more pictures here? Yes, there are. And what should I do? I should tell you about diffraction gratings. So it's so diffraction gratings. The mathematics works just the way it does with the single slit diffraction grating. So point number 1, use the same math from single slit. And that was, if I remember this right, d sine theta is equal to m lambda. That is for the position of the constructive interference. In other words, the bright fringes. The only thing is you have to keep in mind that here d is still the spacing between slits, and there are 2 ways to describe that. You can just indicate d. D is some we'll call it x centimeters. Okay. And that's how it'll be given. But you also might be told that there's a number of slits per centimeter. And so the way that picture might be is that boop, 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 boop. So suppose, for example, this whole thing was, 1 centimeter, and you've got some spacing between individual slits d, then you might not be told what d is, but you might be told that there are n slits per centimeter. And all that means is to find d, you simply take the reciprocal of that. In other words, d would be 1 over n centimeters per slit. And that would be the way that you would compute that. Let's just go back and look at what happens. At least perhaps what I should say is, why would anybody care about using a diffraction grating rather than just a double slit? Well, for one thing, the effect that you get, you'll notice that you get much more intense and much more narrow peaks that makes it much easier to see colors. And the applications include spectroscopy. That is to say, understanding the spectrum of different material. Let's see if I have a picture for this. For example, you use a diffraction grating, and you send in, I guess, what we'll call purple light. It's a mixture of red and blue light, so suppose you don't know what's there. You send that light through a diffraction grating, and what comes out the other side, in the middle, the central maximum is in the same location for all colors, so it's going to continue to look purple. But all the constituent colors will spread out when you go to look at where the first order peaks and second order peaks show up. You'll notice that the blue peaks show up at smaller angles relative to the corresponding red peaks. And so that allows you to figure out what is inside. And I guess the last thing I'll point out is, yes, you can get this kind of effect with a diffraction grating. That is to say, little slits in a material that light is going through. But you can also get the same effect if instead you have a reflective surface, or it's partially reflective. So suppose that it's rough, it's like wood or something not very reflective, but then you put little pieces of reflective material at the same spacing. So for example, a track on a CD is each little track is spaced out by 1600 nanometers or so, and so you'll get reflected light. But because the reflection isn't happening everywhere, it's happening at these special places, then you end up getting your, it's called dispersion of light, the dispersion of the white light into its constituent colors. And that really, that's at the core of what happens when you look at a CD and you notice a rainbow. I don't know if people still use CDs anymore. In case that you haven't gotten a good enough visual for what's going on, again, if you take white light, so that is to say, coming from an incandescent light bulb, something that makes light because it gets hot, like the sun, like an incandescent light bulb, it goes through a diffraction grating. You get all the colors in at the middle bright spot, but then the colors spread out. You'll notice in this picture that you got violet basically at the smallest angle and red at the largest angle. You notice that there's no color that appears any further in. That would correspond to light with wavelength even shorter than violet, and we know that we can't see those wavelengths, so you just don't see it. Here's another visual for you. Again, you get nothing in the middle. You get violet, blue, green, yellow, all the way up to red. Then you get another blank spot because you don't see those wavelengths, but then you see the pattern repeat itself. And I think this is basically a picture we've now seen before. You can pause on it if you like. The top picture shows what happens if you send a combination of red and blue light through a spectrometer. Bottom picture shows what happens when you send perfectly white light through a spectrometer, through a diffraction grating. That's what a spectrometer does, is it really uses a diffraction grating or something like a diffraction grating to disperse the light. And what's the point other than it's cool, you get to make nice pretty pictures? Well, the very cool thing is that if you take pure atomic hydrogen or pure mercury or pure sodium, any pure substance, and you heat it up hot enough and you look at it, you may see a nice bright glow. But then if you let that light come through one of these spectrometers, breaking up the light into its constituent pieces, what you'll notice is atomic hydrogen only has certain colors in it, in very narrow bands. So I guess like purple, blue, orange. And it's a slightly different spectrum for mercury, slightly different spectrum for sodium. When you go to look at the sun, it's mostly white light. You see most of the colors, but through a spectrometer, you'll notice that there are pieces of the spectrum missing. That's where there is absorption by the elements that we know exist in the sun. So have you ever wondered, how do we know that the sun has hydrogen? How do we know that it has trace amounts of, sodium inside of it? Well, notice, for example, that in this solar absorption spectrum on the bottom, that there are these two missing pieces in the yellow area. That corresponds to that sodium emission line. And you'll notice that there's a piece missing over in the sort of orange, and in the blue that corresponds to atomic hydrogen. So this is how you can figure out what's the composition of a star by looking at its spectrum.